London, Marylebone Station, May 1951. The Institution of Locomotive Engineers is holding its summer meeting. There's an exhibition of Britain's most up-to-date locomotives lined up at number 4 platform. Among the giants of the steam age is number 10,100 at its first public appearance. It's a new direct drive diesel of revolutionary construction. And here's its inventor, Colonel Fell. 10,100, now under the disapproving eye of the steam enthusiast, is to make a bid to equal the performance of the steam loco and to better that of its contemporary, the diesel electric.
For 100 years, the steam locomotive held its place unchallenged on the railways of the world. It's difficult to find any machine better suited to its job. It's powerful and sturdily built. With regular maintenance, it has a life of over 40 years. Steam can easily pull hundreds, even thousands of tons away from rest. The train can be accelerated smoothly up to high speeds. All this without the need for a gearbox. But the steam locomotive has its disadvantages. Routine boiler cleaning and getting up steam from cold means that a proportion of its time is spent out of service. It makes dirt. There's the danger of fires from sparks. Only the best quality coal should be used. Even so, the finest steam locomotives only convert 8% of their coal into pulling power. The rest is lost. At speeds like this, over a ton an hour is burnt, and coal supplies are a serious problem in Britain today. The electric train is clean and efficient. The power stations making the electricity burn their coal with 3 times the efficiency of the steam locomotive. But the cost of electrification is great. In Britain, for example, it's only economical on busy routes carrying frequent services. The first gas turbine electric locomotives are on test, but they'll only be an economic job when building and running costs come down. And here's Britain's Royal Scot, double-headed by diesel electrics. Each is really a power station, a diesel engine to drive a generator to supply electric current to the traction motors. 20% of the power developed by the diesel is lost through the electric transmission. Essential because a diesel engine by itself can't pull a heavy train off from rest and accelerate it up to high speeds. This is because the internal combustion engine is not flexible enough. The motor car has a gearbox to provide the speed range. But the car engine has only the weight of the car to pull. A diesel engine cannot be connected to the driving wheels through a car-type gearbox. This would not stand the strain, for a locomotive has the weight of a whole train to move. So far, a combination of diesel and electric motor has been the only way of using the diesel for heavy mainline railway traction. Derby, January 1950. An answer to this problem of direct diesel traction is beginning to take shape at the great locomotive works of British Railways. Locomotive 10,100 is being built. Its design was under the supervision of the chief mechanical engineer of the London Midland region, H.G. Ivett, son of the famous locomotive engineer of the Great Northern Railway. The inventor, Colonel Fell, has worked out an entirely new principle for transmitting the power from 4 standard diesels to the wheels of a locomotive. The Fell transmission system is contained in a special gearbox. Here's an experimental model of it. It's quite unlike a motor car gearbox and uses a novel combination of a well-known principle, the differential gear, familiar to everyone in the motor car back axle. The differential enables the car to turn corners without skidding its back wheels. Though both wheels are driven by the engine through the propeller shaft, on corners, the outer wheel can turn faster than the inner. The Fell gearbox uses the differential in another way, with only a simple alteration to its internal gearing. If a driving motor is put onto one of the axle shafts instead of the wheel, and the other axle shaft is held still, the propeller shaft will turn at half the speed of the motor. Its speed is halved through the differential. Suppose our motor is turning at a speed of 4. Then the propeller shaft turns at a speed of 2. It's been geared down. If a second motor is made to turn the other shaft at a speed of 4, then the propeller shaft will double its speed. It too turns at a speed of 4. This is because the second motor has added its speed to the first, and their combined speeds are halved through the differential. In the Fell gearbox, 3 differentials are joined together like this. 4 diesel engines are put on the ends of 2 of the differentials like this. These 2 are called primary differentials. To start the train, the first engine is allowed to turn its shaft, while the other 3 engines are disengaged and their shafts held still. The speed of this engine is halved through the primary differential and halved again through the secondary differential. Its propeller shaft is geared to the locomotive's wheels. The engine speed has now been geared down from 4 to 1. This provides the right ratio for one diesel engine to start the train off from rest. The second engine is next connected and turns its shaft. Its speed is added to the first engine. This doubles the speed of the locomotive's wheels. The ratio is now 2 to 1. In other words, the system has changed into second gear. The locomotive speed has increased without sliding any gear wheels into mesh, as in a car-type gearbox. The third engine, running at the same speed as the other engines, is connected to the system. Its speed is now added to the total from the other 2 engines, and a speed of 3 is produced in the final drive. This means that the ratio has been raised to 4 to 3. Finally, the fourth engine is brought into play, causing all shafts of all differentials to turn at the same speed. Now the final drive turns at the same speed as that of each engine, and the ratio is 1 to 1. The diagram shows schematically how the gearbox works. In the actual locomotive box, the differentials are arranged more conveniently. The model gearbox shows the same cycle when 4 electric motors, each running at the same speed, are connected progressively to the locomotive's wheels. So, this combination of differentials gives a suitable speed range for a locomotive from 4 to 1 up to 1 to 1, with a smooth transition from one speed to the next, and without the need for a car-type gearbox and clutch. In the Derby works, the locomotive is being assembled. The 4 diesel engines are being fitted into the frame. Each engine is of 500 horsepower. To give them more power and the big pull needed at low speeds, each pair of engines has a supercharger driven from a small bus-type diesel. In another part of the works, the massive differential gearbox is being machined. Special castings for this gearbox were made at the railway's own foundry at Crewe. Each group of gear wheels forming each differential assembly is fitted into place in the gearbox casting. In July 1950, the gearbox was ready for its tests. 4 electric motors take the place of the 4 diesels for the test. Successfully through its trials, the box is lifted into the locomotive frame. It's expected that through this transmission system, only 6% of the power from the diesels will be lost. Each diesel is coupled to the gearbox by a hydraulic coupling. By September 1950, everything was in place, and only the superstructure had yet to be fitted.
On a gloomy November day, locomotive 10,100 took to the rails for her first trial run. In the cab, 4 small levers control the hydraulic couplings which connect each engine to the gearbox. When all engines are in, they're controlled together by the main regulator, which adjusts their power and speed simultaneously. It also uncouples them together when stopping. Soon, locomotive 10,100 was on her proving trials over all kinds of routes. For the first time in the history of British railways, a straight diesel express locomotive was running. The future will decide to what extent she will replace her rivals.